This is David Van Vranken here at UC Irvine, and this is the 24th lecture in the Chemistry 51C series. And we're teaching remotely and learning remotely here on the UCI campus because of the coronavirus shutdown. Yesterday, coming into work, I noticed that there was a house in our neighborhood that had this huge tent over it. I mean, somebody's fumigating for termites, of course. And so I thought I'd talk about what's going on with the termite thing. Maybe a chance to talk about some organic chemistry and the organic chemistry of alkyl halides. But what I realized very quickly is the stuff that's in that tent isn't necessarily organic. So I'm going to tell you about sulfuryl difluoride, which has no carbon atoms in it and is used as a volatile fumigant to kill termite pests. This is not the picture of the house in my neighborhood. They took the tent down last night, so I borrowed a picture from the web. Let's talk about not necessarily sulfuryl difluoride initially, but let's talk about methyl bromide. That at least has a carbon atom in it. Methyl bromide is the main fumigant that they used to use to kill termites in homes when they would put those big tents over those. Certainly in Southern California. But that got phased out in the early 2000s because it destroys atmospheric ozone. Just like chlorofluorocarbons get up into the atmosphere and there's a catalytic reaction by which they destroy ozone. But when I see methyl bromide, I am actually not that concerned about the ozone layer, even though it destroys the ozone layer. The main thing that concerns me when I see methyl bromide is that it's a methyl group that has a leaving group attached. And whenever I see powerful electrophilic methylating agents, I'm not worried about ozone. I am worried about my DNA. You know, there's a lot of irrational fear against chemicals and chemophobia out there because people don't understand the effects of concentration and the idea of a dose-response curve. But there's one class of chemicals that really scares me and that I am cautious about, and that is potential DNA alkylating agents. The problem with this carcinogenic compound, dimethyl sulfate, or an entire class of compounds that generate methyl diazonium ions, we didn't talk about that chemistry in this class, is that they react with DNA. And it's not every part of DNA. It is these little blue atoms right here, and here, and over here, and here, and here. Those are the N7 positions of guanine bases on deoxyguanidinylate residues on DNA. And they are the most nucleophilic site on DNA. And when you methylate those nitrogen atoms through an SN2 reaction, it makes it easy to lose the guanine bases, and that's a source of mutations. You have extremely efficient, I have extremely efficient, we all have extremely efficient DNA repair mechanisms that will replace faithfully those guanine bases, but every once in a while they make mistakes and you get mutations. Now that's not a problem because most of the DNA doesn't actually encode for proteins. And most of those proteins, if you do have a mutation, it doesn't really hurt the cell in some bad way that leads to cancer. But there are some genes that you need to protect, jealously guard, like the gene that encodes for the P53 tumor suppressor protein. Don't mess with that gene. Don't alkylate it. So anytime I see an electrophilic methylating agent, it scares me. And methyl bromide looks like an electrophilic methylating agent. It looks like a carcinogen to me. It's a suspected carcinogen, and which means that, you know, it takes a great deal of effort to prove in a laboratory setting that a compound will lead to cancer. What's odd to me is that I've seen people propose methyl iodide as an alternative to methyl bromide. If you're worried about methyl bromide like I am, I would be really concerned about fumigating or treating crop soil with methyl iodide for all the same reasons that methyl bromide scares me and dimethyl sulfate scares me and methyl diazonium scares me. Now, what did they do after 2005, after they phased out methyl bromide? Well, they replaced it with this chemical combination, sulfuryl fluoride. That was when sulfuryl fluoride was phased in, and it's used in those big fumigation tents as a mixture with a compound called chloropicrin.
Both of these compounds have insecticidal activity, but the real issue here is that sulfuryl fluoride or difluoride is odorless, and it's toxic. You would not want to be exposed to sulfuryl difluoride, so they add another agent, chloropicrin. It's a nitroalkane, except there's no H's on that carbon atom. It's got chlorine atoms. And not only does it have insecticidal activity, but it's a tearing agent, like tear gas. It was initially explored as a type of tear gas in World War I. And so this will strongly dissuade you from being exposed to this mixture, right? You may not be able to detect sulfuryl difluoride until it's damaged you in some way, but chloropicrin, you'll know that it's there. And so why did they add that in there? Well, these tents tend to look kind of interesting to kids, like a circus tent. And kids have this nasty habit of getting into places that look interesting. And so you do not want your kids going into one of those homes that is covered by a fumigant tent, a fumigation tent that looks like a circus tent. And so that chloropicrin will keep any normal mammal or animal from accidentally walking in there. All right, sulfuryl fluoride. Hope you don't get termites in your home. What is it that we've covered in this quarter in organic chemistry? And let me try to review for you what we talked about. So our first exam covered 3 chapters in this Gorzynski-Smith 5th edition textbook on organic chemistry. We started off by talking about electrophilic aromatic substitution. Then we talked about the acidity of phenols and carboxylic acids, mostly using a lot of resonance to explain why oxygen anions would be stabilized. OH compounds are acidic when the O- conjugate base is stabilized in some way. And then there was a little bit of a mention there of inductive effects. And chapter 20 was a super huge chapter. That's when we really started talking about carbonyls and incredibly powerful Grignard reagents and alkylithium reagents adding to carbonyl groups. That's such an important feature of modern organic chemistry. We also mentioned hydroborate compounds, sodium borohydride. Then in chapter 21, we talked about weak nucleophiles adding to carbonyls, a lot of them under equilibrium conditions. Imines by condensation of primary amines with carbonyls, enamines by condensation of secondary amines, acetals, hemiacetals, and then thrown in there was this weird Wittig reaction for making CC double bonds, and you need to know all of those transformations. Chapter 22 was super important especially if you study biochemistry or chemical biology, and that's nucleophilic acyl substitution, making amides, making esters. They really are a reflection of how you make phosphorus oxygen bonds in DNA. And then finally in chapter 23, so that was exam 2, up through enols and enolates, where we showed you how to make enolates using LDA and then alkylating those through SN2 reactions, using enolates as nucleophiles in SN2 reactions. Coming up next Friday, we're going to have our third and final exam, our third and final midterm exam, and that's going to be covering enolates for adding to carbonyl groups. Those are aldol reactions, aldol additions, aldol condensations, Claisen reactions, Dieckmann cyclizations, and Michael conjugate addition reactions, and this weird process called the Robinson annulation. And we just finished talking about chapter 25, which is a chapter on amines. So our exam next Friday is going to cover aldol type chemistry and chapter 24, and amine chemistry, chapter 25, which is a whole hodgepodge. And then the following week after that, we've got our final exam. It's optional. If you choose to take the final exam, we will use your score on the final exam automatically to substitute for any score that is lower on one of your 3 midterms. If you don't have to take the final exam if you don't want to. We won't use the final exam score to lower any of your scores. If you take the final exam and score a 1%, we won't substitute that for something that's higher. It's only designed to help you if you'd like to. So I hope you'll take the final exam. It's good practice for just kind of studying. And it's comprehensive for the chemistry for the whole quarter. All right, let's try to start reviewing here. What is it that we've been covering all quarter? Well, we've covered so much material. Just think back to your first quarter of organic chemistry, where basically you just learned SN1 and SN2 and E1 and E2, and that was it. My gosh, that was so few reactions. And then we just covered 1 million of them this quarter. Let me just go ahead and remind you of what we covered in chapter 18. We talked about 5 important electrophilic aromatic substitution reactions. And I'm going to go ahead and change this to note the fact that you now know 6. I'll just write plus 25. You now know a 6th electrophilic aromatic substitution reaction that comes from chapter 25. There's 6 of them, but the ones you learned in chapter 25 are halogenation. Right? You can add halogens to aromatic rings, or if you wanted, you could use Cl2 and FeCl3 for adding chlorine atoms. It's the same recipe. You substitute an H for a bromine atom. The other thing that we learned in that chapter is how to make carbon-nitrogen bonds on benzene rings, and that's you substitute H's using this recipe, nitric acid and sulfuric acid. I expect you to know all of these recipes. And probably the most powerful carbon-carbon bond forming reaction for substitution of H on a benzene ring is Friedel-Crafts acylation, where we use an acid chloride and aluminum trichloride. And you also learned another variant. Well, let me put that down in the alkylation. But Friedel-Crafts acylations are usually well controlled. Those are the 3 most useful bond forming processes: forming carbon halogen bonds, forming carbon nitrogen bonds, and then forming carbon-carbon bonds. We also introduced this reaction that allows you to make carbon-sulfur bonds. I mentioned this drug that Alexander Shulgin had made that has a carbon-sulfur bond in there. You know, it starts with electrophilic aromatic substitution with sulfur trioxide before you can reduce that down and make a fancy designer drug out of that. The last reaction that we talked about, the last recipe, was Friedel-Crafts alkylation, where we use alkyl halides and aluminum trichloride. And you know, any way that you make a carbocation, whether it's ionizing off a hydroxy group or some other process, or protonating an alkene to generate a carbocation, will lead to things that can attack benzene rings. And then recall that last recipe that we talked about, where I just barely have room to fit that in here, where we talked about the use of diazonium ions, I'll write AR for an aryl group, where you had an arene diazonium ion, and then it forms an azo linkage on your molecule. And I'll just write AR there for generating it's a new recipe. We just finished covering that in chapter 25. So you have 6 recipes for doing electrophilic aromatic substitution of protons on arene rings. Now, I expect you to know the mechanisms for those Friedel-Crafts acylation reactions. I expect you to know the mechanisms by which you generate those electrophiles, whether it's a nitronium ion or a protonated SO3 or an acylium ion. Know those mechanisms. And so let me just remind you of the mechanism for these processes. So, right, if I ask you what's the arrow pushing mechanism for these reactions, and you know, there's going to be some sort of mechanism stuff on my next exams. Remember, in the sapling homework system, I've told you to only draw 1 lone pair if it's needed, and if you don't need a lone pair in the mechanism, then don't draw any. But at most, in any arrow pushing step, you need 1 lone pair and never more. So, right, if I were to draw this out, I would draw the lone pair starting here and attacking the chlorine. That would be step 1. And so here I've drawn that for you. So chlorine atom has a lone pair, and it adds to aluminum trichloride, and it generates this species that just looks absolutely crazy. Look at those 2 bonds to chlorine right there. You've seen that before. So let me just remind you of where you've seen chloronium ions before. Way before this chapter. Let me do this in black just to remind you of where you've seen that before. Way back in chapter 10 in the Gorzynski-Smith textbook and in the 2nd quarter of organic chemistry, you learned about these reactions where you take alkenes and you react them with halogens, with Br2 or with Cl2. And there's this process where you start by attacking and pushing out chloride anion. That's supposed to be a chloride up there. And then these lone pairs come back and you generated this cyclic 3-membered ring intermediate called a chloronium ion or a bromonium ion. So you have seen halogens before with 2 bonds and a positive charge. So this shouldn't be that freaky to you, but maybe it is. But as soon as I see this, I want to use that Cl plus as a leading group, and it turns out the lone pairs on the other side of the carbonyl just bend over and push that out from the back side. And that's what leads to this acylium ion intermediate. It's a super important intermediate. And it's not a crazy intermediate. Every atom here has an octet of electrons. The oxygen has 8 electrons. There's a lone pair I didn't draw here. So you generate this acylium ion that's more stable than a T-butyl carbocation because every atom has an octet. And you generate this tetrachloroaluminate counterion. And in the next step of the reaction, you add to an aromatic ring, to the pi system of an aromatic ring. And so I have those arrows already drawn out for you here, where you add to the acylium ion, you don't add to the O+. Don't do that, it's already got 8 electrons. Add to the carbon and move one of the pi bonds to the O+. And so that leads to this species called an rhenium ion intermediate. We go ahead and write out rhenium ion. We've seen so many of these now, I hope. And I hope you know these general 2-step mechanisms for electrophilic aromatic substitution. But now any species can come along and pull off a proton because this really wants to be aromatic again. In general, in the mechanism, it's this tetrachloroaluminate that's doing that. But we're just symbolizing that by saying A- to acknowledge the fact that the conditions are acidic. And so that's the 2-step mechanism. And I expect you to know those 2-step mechanisms for electrophilic aromatic substitution and all the mechanisms for generating those electrophiles in electrophilic aromatic substitution reactions. Super important concept in chapter 18. Now, some aromatic rings, most actually, have substituents on the ring. And you need to know if you're talking about adding another substituent, a second substituent, or a third substituent, you need to know whether reactions are faster or slower or occur at all. And you need to know what is the regiochemical directing effect of having those substituents on there. So let's go ahead and talk about that because I gave you this list that you have to memorize. It's a ranked list starting from the most activating substituents that you can have on a benzene ring to the least activating substituents that you can have on a benzene ring. And what we told you, so I've divided this up here in terms of relative to just having an H on a benzene ring. A benzene ring has 6 H's. So it's kind of like having nothing extra. So all the substituents I have above here are more and more and more activating. You would expect these substituents to accelerate the rate of electrophilic aromatic substitution. And all of the substituents below here are increasingly deactivating, so go slower and slower. So when you walk from the top of this list to the bottom of the list, these substituents make electrophilic aromatic substitution of a second group, adding a second group, harder and harder and harder and harder on that aromatic ring. And it's really tough once you've got a nitro group on your benzene ring to add another substituent. You have to have really aggressive electrophiles like nitronium ion to add a second group if there's already a nitro group on there. Now, there's almost a perfect correlation between whether substituents activate benzene rings or deactivate and whether they are ortho, para, or meta-directors. And let me just remind you that anything like halogen or more activating is going to cause the next substituent to go ortho or para. Here's what that means. So if I have a phenyl group on a benzene ring, and we'll just write EG here, right? If I have a phenyl substituent on the benzene ring, then that's going to cause the next substituent to go ortho or para, right? An aryl group, phenyl is an ortho para director. So the next substituent you add to this ring will go, right? Phenyl is identical. So it'll be happening on both the rings here. If they're, if it's just a simple phenyl. If it's a deactivated phenyl, then you add to this ring. So you add to the ortho or para positions when you have an ortho para director, and all of these here are ortho para directors. When we come down here, so it's unfortunate because it would be super easy to memorize if X compounds were activating substituents, because then all activators would be ortho para directors. Now, remember down here, anything less below halogen substituents in this list are meta-directors. They cause the next substituent to go to the meta position. So for example, if we had a sulfonic acid on here,
and then we added a nitronium ion or something like that, that next substituent, this thing slows down reactions at the ortho and para positions. It's not that it makes it faster at the meta, but it slows down the ortho and para substitution. So you end up with meta direction, you end up with meta substitution by default. You add the next substituent to this, a second substituent, it goes to the meta position. And there's two meta positions here. So these are all meta directors. So one of the other issues that we brought up is that this helps you to understand the limitations of the Friedel-Crafts reactions. So remember, T-butyl carbocations or acylium ions are not as aggressive as nitronium ions or protonated SO3. And what you find is that we have exceptions here. You don't do any, you're not going to be able to do any Friedel-Crafts if you have one of these meta directors on your benzene rings. They're all 2 deactivated. So I'm just going to write here as a little note to you. Remember, no Friedel-Crafts. Don't do Friedel-Crafts if you have any of these deactivators, anything below. You can do it if there's a halogen on there. But there's another weird case where you can't do Friedel-Crafts. And that is over here when you have amino groups. Not amides, but amino groups. You can't do Friedel-Crafts if you have an NH2 or an alkylamine. That's because this nitrogen atom will add either to the electrophile itself, or else it'll add to the aluminum trichloride. And once you add to that, you basically convert the nitrogen atom into one of the strongest deactivators. So you don't do no Friedel-Crafts over here either. Remember that. So there's only this kind of limited, narrow range of functional groups you can have on that benzene ring that allow you to still do Friedel-Crafts. And some people have asked me before, well, can you do Friedel-Crafts if you have a super activator and a super deactivator? You can't know that. I'm never going to ask you that question. You'd have to look that up in we have these reaction databases where I'd have to look that up to know if you have both an activator and a deactivator, then can you do Friedel-Crafts on the reactions? I wouldn't ask you that. We never gave you enough information to address that issue. These rules are only if you have one, two of the same, one substituent, or maybe 2 of the same kind of substituent, like 2 deactivators. Then of course you couldn't do Friedel-Crafts if you have 2 nitro groups on a benzene ring. Okay, you have to know that ranked list. You have to. There's no way around that. Okay, so let's go ahead and talk about, it's weird, I'm not quite sure why I had this other, I had another slide here, and I'm not quite sure why I have this, because this looks like the same slide. But you have to, this is because we want to talk about when you have 2 substituents on a benzene ring. Then how do you decide where the 3rd substituent is going to go? And let's go ahead and talk about that. I'll go ahead and paint out a picture here where we have an oxygen substituent. Who cares what the alkyl group is? We'll make that an isopropoxy group. And then maybe a methyl group on there. And if we add a 3rd substituent through Friedel-Crafts, where does that substituent go? And in order to decide that, the rule is that if you've got 2 substituents on there, the most activating substituent controls the regiochemistry. So the substituent that is higher on this ranked list that I told you have to memorize is the one that controls the regiochemistry. So let's look at this benzene ring. It's got an oxygen substituent, that's OR, and it's got an alkyl substituent, that's down here. Well, the OR is higher on this list. It's going to control the regiochemistry. And so that means that the 3rd substituent you add is going to go ortho or para to the oxygen. Well, the para position's blocked. So the only place you could really go with this is that you would end up substituting on ortho to the oxygen. So if we took some reaction, I'm going to go ahead and draw this out with a black pen here, like chlorination and FeCl3, then that's going to go ortho to the alkoxy group. The alkoxy group controls the regiochemistry. It's the most activating group on there. So the 3rd substituent goes ortho to the alkoxy group. Some people get confused. They think, oh, well, I thought meta director means that my next substituent goes meta to everything. No, that's not what it means. It means that the next substituent after this one is directed to go meta. or the next substituent after this one is directed to go ortho-para. So these ortho-para and meta-directing effects are for the next substituent that you add. All right, you have to know those rules, and I can't imagine giving you a final exam that doesn't ask you about Friedel-Crafts reactions, or again, I don't know what I'm going to put on the final exam, but every final exam that's taught in an organic chemistry class is going to ask you something about, I think, about Friedel-Crafts reactions, or it's a pretty important common reaction. You know, there was after the Friedel-Crafts chapter, there was this chapter on the acidity of OH compounds. And just in general, there's a set of pKs that I expect you to know. I expect you to know those numbers numerically. I expect you to know the rank order for those compounds. And I think before I cover that, you know what, let me stop. Let me stop and talk about some other synthetic transformations of aromatic compounds before I get to that. Sorry for that. So let's talk about some other synthetic transformations that they had in this chapter on electrophilic aromatic substitution. So after you do electrophilic aromatic substitution to make ketones or to make alkyl groups, there's other things you can do. We told you about some reduction methods for reducing carbonyl groups down. One was this Clemenson reduction that we've talked about before. I think I showed you this thing with hexyl resorcinol that they put into secrets. So for that case, you can use zinc-mercury amalgam, but you have to use strongly acidic conditions for those. Those are run in hydrochloric acid, and you have to heat them to get them to go. There's no mild conditions for reducing a carbonyl group down to a CH2 group. Remember, this is an alternative. There's an alternative procedure. If your compounds are stable to harsh base, use hydrazine and sodium hydroxide and heat. Just as good. And if your compound is not sensitive to acid or base, then you get to choose either one that you want. Now, we had to caution you that you can't make compounds like this by direct Friedel-Crafts alkylation, because if you tried to do that, you would end up initially generating a T-butyl, a primary carbocation that would undergo hydride migration. Let me go ahead and draw that out. I think we might have had this on one of the exam problems. But this primary carbocation wouldn't be stable. You would end up getting, it's kind of, I always feel like I like to draw the things that are attached to my carbenium ions, my carbocations. So let me draw the fact that there's two H's on there. If you generated this, it would immediately, before it could attack anything, it would immediately undergo a hydride shift, and you would get this very rapid conversion to a tertiary carbocation that then would have the lifetime it needs to add to an aromatic ring. And so this is what would end up adding. If you try to do direct Friedel-Crafts alkylation with this alkyl chloride, you would end up getting as a substituted product. I hope I can fit this in here. This quaternary center with no hydrogens on there, because you can't stop this 1,2 shift. That 1,2 shift is too fast. So don't try to do Friedel-Crafts reactions with primary alkyl halides if they can do hydride shifts or even alkyl shifts sometimes. Hydride shift is usually faster. Okay, so another reaction that we taught you in chapter 18 was the reduction of nitro groups to make amino groups. And if there's no halogens on the ring, that's super simple. You just use hydrogen and palladium on carbon. If there is a halogen that you want to keep on there, then you have to use that tin hydrochloric acid reduction. A little clumsier, but this is so simple. You just evaporate, you filter off the palladium and evaporate all the solvents, and you've got pure amine and 100% yield. Boy, as soon as I generate an arylamine, I want to make amides out of that, or I want to convert it to an imine by reacting it with an aldehyde, or I want to convert it to a diazonium reagent by adding sodium nitrite and HCl. So many things you can do with these anilines. That's really a useful synthetic transformation to put nitro groups on benzene rings and then to reduce those down to amines. Now there's one other reaction that we talked about which is super important, and that is to do free radical halogenation of the benzylic position on a benzene ring. And it involves, you don't have to use N-bromo-6-cinnamide like for doing an allylic CH. For benzylic CHs, you can use Br2. If you wanted, you could use N-bromosuccinimide. And then some initiator like peroxide, heat, or light. I don't know why the book gives you so many different combinations. It just doesn't make any sense to me. I'm going to give you bromine and light. You bring it in the lab, you put bromine in there, and you bring this lamp out, and you shine it over your flask. We have very special high-powered things. But the reason why this is important is you're now set up for two different things once you put a benzylic bromine on there. One thing that you can do is SN2 reactions. Substitute it with a nucleophile, an alkoxide, a thiolate anion, a cyanide anion if you wanted. You could add sodium cyanide and do an SN2 reaction. So benzylic halides are extremely reactive for SN2 reactions. But that's not really the interesting thing that you can do there. The thing that's really interesting is converting that into a super powerful nucleophile, right? It can be a leaving group, or you can make it into a super powerful nucleophile. Just add some magnesium in there, or lithium. And now you've got a Grignard reagent. You've totally changed the character of that now. And now you can add that to carbonyls. Oh yeah, I really want to add that to a carbonyl, or two equivalents of that to an ester. So putting a benzylic halogen on there is really useful as far as your synthetic repertoire. Okay, now let's talk about chapter 19. Acidity of OH compounds. And again, you need to know the acidities the relative acidities of organic compounds. Now, chapter 19 is mainly about oxygen acids. And so probably one of the most important pKs that I expect you to know is the pK of water or an alcohol. You need to know that. So the pK is somewhere on the order of 16 for water and for any typical alcohol. And what chapter 19 talks about is, well, how do you rationalize why phenols are so much more acidic? Well, you have to draw out the conjugate base. There's no way to explain, and I don't have time to draw those out, but how do I express that this is a million times more acidic? Depends on the substituents on there. I'm going to go ahead and write a pK of 10. That's the pK I expect you to know for phenol. That's the side chain of the amino acid tyrosine, has a pK of 10. It's a million times more acidic because the O- is resonance stabilized. You can push the electrons into the benzene ring. I expect you to know that carboxylic acid's like acetic acid, like vinegar. That has a pK of 5. That's 11, these are orders of magnitude. That's 11 orders of magnitude more acidic than water, or than ethanol, or isopropanol. So way more acidic. That's why it's called acetic acid. Then finally, we get down to some serious acids, like sulfuric acid or toluene sulfonic acid. This has a pK of -7. Minus. Let me make that really dark. -7. Man, that is a crazy strong acid. So toluene sulfonic acid is a solid. It's the same for hydrochloric acid. So now we're talking, what is this? 16 minus -7. That's like 24, 23 orders of magnitude more acidic than water. So it matters what's attached here. And again, to explain why those relative acidities for these various compounds, you need to recognize the possibility for resonance. Okay, since chapter 19, we've talked about some other types of acids, and I expect you to know the pKs. I expect you to know these numerically, but especially I expect you to know the rank order of these. So we talked about these classes of CH compounds that are so acidic that if you form the carbanion, you can't even protonate it by putting it in water. So with 2 carbonyls on this CH compound, it becomes so acidic that you can't even protonate that by putting it in water. It's amazing. The pK for this compound here is somewhere on the order of about 11, depends on exactly on the substituents, 11 to 12. But it's so easy to form the anions here. This is what we used to do in the 1960s and 50s before we knew how to use LDA to make enolates. We had to make super stabilized enolates that you could put in water or in alcoholic solvents and then use them for SN2 type processes. But right around the 1970s, they developed LDA so that you could take any carbonyl compound, ketones, esters, amides that don't have NHs on them, and to deprotonate these with LDA. And a typical ketone has a pK somewhere in the order of about 20. And it depends on what's on the other side here for how acidic that is. An ester would have a pK of about 25. And I expect you to know those. And 25 is kind of an interesting number because that's the pKa for an acetylide anion. Whoa, oh, I didn't mean to write that in a black. Sorry, 25. So, and you learned how to make acetylide anions using sodium amide kind of in chapter 12 of our textbook. We introduced you to this idea that sodium amide, NaNH2, can deprotonate terminal alkynes to make carbon nucleophiles. And then you didn't do anything interesting with them. But now that you know about addition to carbonyls, you can add those acetylide anions into carbonyls. Now, it is extremely difficult to deprotonate NH on just an alkylamine. The only thing that can do that is butylithium. That's how you make lithium diisopropylamide. The pK for amine NHs varies. I'm just going to give you a number 35. It depends on the alkyl substituents. And again, only butylithium can pull that off. Not sodium hydroxide, not potassium T-butoxide. Nothing else we've ever taught you about can pull that off effectively except butylithium. And then finally, when we get to typical CHs, you know, there's no reagent we're ever going to give you that allows you to just pull an H off of an alkane. You know, they sell alkylithium reagents in pentane because you can't just pull a proton off of an alkane. So the reason why this order is so important is not because we necessarily care about the acidity of all these compounds. It's because this order that I've given you, where I arrange things by pKa, is also the order of nucleophilicity of the conjugate bases. So when I draw out the conjugate base and I try to assess what is the range of nucleophilicity here, the nucleophilicity of these conjugate bases spans 57 orders of magnitude, just like the pKas of the acid forms. So if I were to talk about the relative nucleophilicities of these, it would be at the low end of the scale, 10 to the minus 7. Over here, the conjugate acid for this would be 10 to the plus 5, way more nucleophilic. Not that you'd ever use that it's not very common to use acetate as a nucleophile. You get to phenoxides, now we're talking about things that you might actually use for a nucleophile. I think they used to do that in the chemistry 51 labs here at UC Irvine to attack chloroacetates to make things kind of similar to Agent Orange. But now we're talking in a relative sense, 10 to the 10th, 17 orders of magnitude more nucleophilic than a tosylate anion, which isn't ever going to act as a nucleophile in any reaction you would ever see. And then relative to that, we have this carbanion, the stabilized carbanion, which is more nucleophilic, about an order of magnitude more nucleophilic than a phenylate anion. And then alkoxides are more nucleophilic than these carbanions. Unfortunately, as we get higher and higher, it turns out that basicity becomes important, and you start seeing competing elimination processes or competing deprotonation processes as we go higher. So, right, I'm just going to take this and raise it to the power of the pKa for the conjugate acid, and it tells me how nucleophilic these species are in a relative sense. So it's important for you to know the rank order of these various species. And finally, we get up to an alkylithium. It's kind of like a carbanion plus a lithium plus. This is the relative order of nucleophilicity and basicity. So let me just write and basicity here. Basicity and nucleophilicity are usually in parallel. You know, lone pairs that are good nucleophiles are usually good bases. And I expect you to know this order. I expect you to know that an alkylithium is a vastly more powerful nucleophile than an alkoxide. You just have to know those, and pKs tell you something about that. Okay, you know, there are trends here that I expect you to understand, not just memorizing a bunch of numbers in a ranked list. You know, there are some trends that we could rationalize based on the periodic table and based on electronegativity. And so I want you to understand how electronegativity affects pK. So the way you compare molecules and their pKs, you have to draw out the conjugate bases. So if I ask you to think about which of these ought to be more acidic, the OH, the NH, or the CH, you really need to draw out the conjugate base of each of those and ask which of these likes the extra electron density more. And the O minus loves having that electron density. It's less reactive. It's less reactive because it's electronegative, less reactive, it's less nucleophilic, and it's less basic. Nucleophilicity and basicity are types of reactivity. So I'll just put that less basic there. So, right, this is, because oxygen's more electronegative. It loves that negative charge. Carbon hates that negative charge. Man, is that alkyl-anion reactive. If you could make a naked alkyl-anion, you would expect them to have nucleophilicities that parallel the acidity here. You'd expect a relative nucleophilicity here, or basicity of 10 to the 16th, or 10 to the 35, or 10 to the 50. These are log units. I mean, 10 to the 50. Have you ever like, those types of numbers are so far outside are the realms of human experience. We also expect you to know how resonance affects nucleophilicity. So if we have two carbanions, but one of them is stabilized by resonance, like this enolate over here, remember there's a resonance structure we can draw for this. It looks like this. That ability to donate, the ability of this lone pair to donate into the carbonyl makes that lone pair less reactive. Enolates are still reactive. They're still reactive right here on this end carbon. That's where they form bonds. And the reason, but it's way less reactive than an alkyl lithium. An enolate is way less reactive than a Grignard reagent. About how much less reactive? Well, I'm just going to take it 10 to the power of the pK for the conjugate acid. If this is in relative terms 10 to the 20 nucleophilicity, and this is 10 to the 50, you'd predict that the alkyl anion is 30 orders of magnitude more nucleophilic than an enolate. And that makes perfect sense. Man, that's hard to imagine. 10 to the 30 is such a huge number. And finally, we get here in chapter 19. This is what chapter 19 was really about, is oxygen acids. How does resonance explain the fact that carboxylic acids are 100,000 times more acidic than a phenol, right? It has to do with the resonance structures. Over here with a carboxylate, if you deprotonate a carboxylate, let me draw these deprotonation events over here. If you deprotonate a carboxylate, the resonance structures you can draw are super stabilized because I can put in this resonance structure the negative charge on another electronegative oxygen atom. That's a great resonance structure when I can put the negative charge on an oxygen atom, because oxygen's electronegative. But over here with a phenolate, there is resonance stabilization to this O minus, and I can draw more resonance structures, but none of them are really as good as this first resonance structure with O minus, because these other resonance structures are not aromatic anymore. So I can certainly draw more resonance structures here, but right, that's not an aromatic ring system. It's not 6 electrons in a cyclic array, because it skips where there's this carbonyl, this double bond sticking off the side of the ring. So pushing the electrons onto another electronegative atom is certainly, if I look at the relative nucleophilicity of all these species here, this would be 10 to the 5, right? The pH is 5. This would be 10 to the 10. And an enolate, where I push the electrons onto a carbon atom, it's not as stabilized. It's more reactive. Enolates are more reactive than an acetate. So this may look like a lot of pKa's, but it's important for you to know the relative sense, how much more reactive one compound is over the other. And a lot of times electronegativity and resonance can help you explain trends. I'm going to go ahead and stop right there, and we'll try to see how far we can get with this review material on Monday and Wednesday of next week. Again, keep working problems to get ready for that exam next Friday. It's going to cover chapter 24 on aldol reactions, Claisen, Dieckmann, Michael additions, and then this whole chapter on amines with reductive amination and diazonium ions, and a review of other carbon-nitrogen bond-forming processes, the Gabriel synthetic sequence. So stay safe, stay sane, and I'll see you guys on Monday.